we are going to be going over the history of atomic theory and isotopes. We're going to be looking at the different atomic models.
Like Hiroshima and stuff.
So, investigating atoms and atomic theory.
Should be able to describe the particle theory of matter.
So, atomos is the Greek word meaning not to be cut. It's the word that the atom comes from.
Like can't be separated.
But it can be separated if it makes atom bombs.
Yes. So, now we know that they can be separated.
Didn't Albert Einstein think the formula do that?
It was before Einstein that we knew that atoms can be divided. So, this model of the atom may look familiar to you. This is known as the Bohr model. In this model, the nucleus is attained by electrons, which are in different energy levels. A model uses familiar ideas to explain unfamiliar facts observed in nature. A model can be changed as new information is collected. Model doesn't have to be correct to be useful. We actually still use the Bohr model a lot of time in working doing chemistry, even though we know that the Bohr model is wrong. The Bohr model is not the correct way of looking at the atom, but it is still useful to use the Bohr model in working out chemistry. So, the atomic model has changed throughout the centuries. We're going to start in 400 BC when it was first theorized about existing. Cody, stop talking. These are the people who contributed to the development of atomic theory. So the first person in 400 BC is Democritus. I'm pronouncing it wrong. How do you say it?
Democritus.
Democritus. Cody, quit talking. So this is the Greek philosopher who began the search for a description of matter more than 2,400 years ago. He asked a simple question. Like a lot of great philosophers at the time, they usually came up with profound thought experiments, and he asked a simple question. Could you divide matter into smaller and smaller bits forever? Can you take a rope and continually cut it into smaller and smaller bits? Can you take a rock and half it over and over and over again? Or is there a certain limit in which you cannot cut it any smaller? Is there a finite number of times a piece of matter can be divided? He thought that there was a limit, that eventually you would reach a piece that would be indivisible, that cannot be cut anymore. And he called this atomos. Matter could not be divided into smaller and smaller pieces forever. Eventually, the smallest possible piece would be attained. So he named it atomos, meaning not to be cut. To the Democritus, atoms were small, hard particles that were all made of the same material, but were different shapes and sizes. So different atoms were of different shapes or different sizes. Atoms were infinite in number, always moving and capable of joining together. And how well do y'all know y'all's Greek history?
Decent. The boys know it really well. They study
So, this theory was correct, somewhat, but it was largely ignored and forgotten for more than 2,000 years. Why was it ignored for 2,000 years?
because they had a technology to experiment.
No. Who was around Democritus' time, 400 BC?
Rome. No.
Jesus, a lot of people.
I was kidding.
I was
Who?
kidding. That was
Name some
not-
Greek philosophers. Who are the most famous Greek philosophers?
Poseidon.
Philosophy.
No.
As a god?
I just said it. You know, I just thought about it. Galileo.
Galileo. And
Albert Einstein.
No.
The one that ran out of his bathroom. Leonardo DiCaprio. That's the one. Bob Ross.
Aristotle.
Jack.
And who else besides Aristotle?
I don't know. Something that.
Plato.
Pluto.
So during the time, there was two philosophers who were greater known. Aristotle and Plato. They had many correct theories and made a huge impact on the nature of science. Them two believed in an alternative theory, fire, air, water, earth, combinations making up the elements. Just a second. So, because they were so right on all the other theories, no one doubted that they were wrong on this. And so, for 2,000 years, we believed on the elemental theory that everything is combinations of fire, air, water, earth, and then a fifth one, ether or spirit. What was your question?
Oh, how come they chose fire as one of them?
Because it's heat and fire.
So it just heat and you know.
Like, for example, lava was a combination of earth and fire.
I got it. But I understood.
Steam would be a combination of water and air mixing together.
So basically, they're good.
No, this theory is completely wrong.
Well, I mean, Earth can be metals and stuff like that, right?
Yes.
And then you use fire to smelt them down and whatever, right? So
But just raising their temperature in general, you can do it without fire.
How?
Easy. Ever heard of friction welding?
Another thing. Look, we didn't have that technology back then. But still, Earth could use Earth materials to make it.
So, Greek model 400 BC, and then Aristotle's four elements dominated for 2,000 years. And modern atomic theory doesn't actually begin until 1800s. In the early 1800s, the English chemist John Dalton performed a number of experiments that eventually led to the acceptance of the idea of atoms. So, the original theory of atoms was discovered in 400 BC, but because of Aristotle's four-element theory that was supported by Plato, it took 2,000 years for them to realize it's wrong, or for them to actually rediscover the atomic theory. John Dalton basically set up the groundwork for all of chemistry. He deduced that all elements are composed of atoms. Atoms are indivisible, meaning they can't be divided, and indestructible particles. Atoms of the same element are exactly alike. Atoms of different elements are different. And compounds can be formed by joining two or more elements together. So water, you take two hydrogen atoms and an oxygen atom, you put them together, you get water. Which is a huge leap, and is basically the foundation of modern chemistry. But we realized that atoms can be divided. there are particles smaller than an atom, but his work, John Dalton's work, is fundamental to chemistry. The fact that he came up with the fact that compounds and atoms really exist, and that how he worked to make compounds turned out to be true. He was just wrong that atoms can be, and take your hoodie off, that can be divided. Michael, lift your head up. Put your mask on. The next guy is J.J. Thomson. So in 1897, the English scientist J.J. Thomson provided the first hint that an atom is made up of even smaller particles. He proposed a model of the atom that is sometimes called the plum pudding model. Atoms were made of a positively charged substance with negatively charged electrons scattered about it like raisins in a pudding. So his theory can be thought of as a gelatin with the gelatin material being positively charged with tiny electrons scattered throughout it and suspended. How he discovered it was, so they knew about electricity, but they didn't know what electricity was.
That makes sense.
They knew about charges and everything, but they didn't know about atoms and electrons. J.J. Thomson is credited as discovering the electron. He passed an electrical current through a gas. He noticed beforehand that there was no charge in the gas, and then when he ran an electrical current through it, he noticed a charge. As the current passed through the gas, it gave rays of negatively charged particles. This surprised him, because the atoms of the gas were uncharged. Where had these negative charges come from? He realized that the only possible source for these electrons, and Michael, lift your head up. The only possible source of these electrons had to be from within the atom of the gas molecules. They actually had to be inside the gas particles. Thomson concluded that the negative charges come from within the atom. A particle smaller than an atom had to exist. The atom was divisible. Thomson called these, and I'm so glad this name didn't stick, negatively charged corpuscles, something like that. Really hard to pronounce word. Today we know them as electrons. Since the gas was known to be neutral, having no charge, he reasoned that there must be a positively charged particle in the atom, but he could never find it. So he never saw the electron, he just knew that they had to exist based on experimental data. By the way, this device that was pictured is known as a cathode ray tube.
Do we have one of those?
No, we don't.
Can we get one?
It's... Yes. So we have this stream, this paper here that glows whenever electrons hit on it. Basically the setup of a cathode is we have metallic plates that can steer electrons.
So the paper's blushing.
It's a vacuum inside of it, basically, with a small bit of gas.
But it's blushing because the electrons are hitting on it.
Basically, we have a source that can produce electrons or charges. And then we have deflector plates that can control where they go. This is the one more like the one he used. But it's known as a cathode ray tube. So you use cathode ray tubes to discover the electron. So, next guy is Rutherford's gold foil experiment. In 1908, the English physicist Ernest Rutherford was hard at work on an experiment that seemed to have little to do with unraveling the mysterious mystery of the atomic structure. By the way, these people who are given credit are not technically the people who discovered it, they're just given credit for it. Does anyone know why that is? Why does it say that he discovered it? So, when you go to college, if you work on a doctorate program to get your PhD, as a PhD student, you're working under a professor, and any work you do is often credited to your advisor or your professor above you. So, I believe in this case, it's Rutherford's two students that are doing this, but Rutherford's given the credit. I'm not entirely sure on the history of this. You'd have to look it up. I'm just mentioning this, that some of these...
So
Yeah.
you're saying that if me and Cody discovered a new species, you would get credit?
If I'm paying you and funding your salary and you're living, the only reason you're living and working on it is because I'm allowing it, I expect any work you do would be given to me.
No, man.
Just like, if you were to go out and hit the lottery, I believe your parents can claim the money.
My mom would do that. She would take it and put it in the bank.
Yeah.
She wouldn't, like, take it and spend it.
Because I think, like, child actresses and actors,
I have no control over their finances.
yeah, the parent can get it.
Oh, yeah.
Michael, lift your head up.
It's okay.
And pay
that
attention.
money's gonna be gone by the
Like,
time-
raise it up. It's up resting on your arms. So, his experiment was, he fired tiny streams of positively charged particles known as alpha particles at a thin sheet of gold foil. Remember, gold is extremely malleable. You can hammer it down to only a few atoms thick. He had about a gold foil that's only 2,000 atoms thick. So a fraction of the width of a human hair, how thin it was. Now, this experiment, I like this experiment because it's described as taking a 9mm pistol or a rifle round and shooting it at a piece of paper and seeing the round bounce off the paper.
Oh, so you want to shoot them?
Yes, and that's how shocked they were. So he basically did very high energy alpha particles that were basically charged bullets, and almost all of them passed right through the gold atoms of the sheet without even changing course. So they passed straight through it as if they hit nothing. Some of the positively charged bullets, however, did bend, and that's what they were trying to do. They were trying to determine any amount of deflection, but they saw something that was completely shocking. Some of these highly energetic charges bounced off the gold foil. They ricocheted when, as if they had hit something solid. Again, before Rutherford, the idea was that they're basically a positively charged substance, like gelatin. They're basically shooting ballistics gel. And that's what they were thinking, and all of a sudden it ricochets off the ballistic gel. This told them that it had to hit something solid and very dense. They knew that positive charges repel positive charges, so Rutherford is credited for discovering the nucleus of an atom. He basically set up this system and noticed that a few of the alpha particles bounced off of something, and it had to be something that was highly positive and very dense. So basically, occasionally an alpha particle would hit the nucleus of an atom and ricochet off. This could only mean that gold atoms in the sheet were mostly up in space because almost nothing reflected or changed direction. And atoms were not a pudding filled with positively charged material. Rather concluded that an atom had a small, dense, positively charged center that repelled his positively charged bullets. He named the center of the atom the nucleus. And put your mask on correctly. The nucleus was tiny compared to the atom. Rutherford reasoned that all of the atom's positively charged particles were contained in the nucleus. The negatively charged particles were scattered outside the nucleus around the edge. So basically, I will say this. So Rutherford is given credit for the discovery of nucleus. We also give him credit for protons, although he knew nothing about them. Him and his students under him eventually went on to discover protons, I believe. But basically, also one of the things he's shooting is an alpha particle, which is composed of 2 protons and 2 neutrons. So 2 protons, 2 neutrons is an alpha particle. By the way, does anyone know what it's also equal to? What is an alpha particle, really? What has 2 protons? Not hydrogen. Helium nucleus. It's just a helium nucleus. And it's hardly even spelled. It's just a helium nucleus without any electrons. Radioactive materials usually emit alpha particles when they decay. So his model was there was a positively charged substance. Protons there's positively charged particles in the middle, so a nucleus, and the electrons are all on the edge surrounding around it. I mean, they make a shell, so electrons are in a shell around the electrons are on the edge. Edge of atom. And mostly empty space. Which brings us to the Bohr model, a very useful model that we'll use throughout this class. In the 1913, Danish scientist Niels Bohr proposed an improvement. In his model, he placed each electron into specific energy levels. According to the Bohr's atomic model, electrons move in definite orbits around the nucleus, much like planets circle the sun. These orbits or energy levels are located at certain distances from the nucleus. So it's also called the planetary model. You can think of electrons as orbiting around the nucleus. It's a very useful model for describing the atoms. So, for example, carbon. We have a nucleus. Carbon inside the nucleus would have so 6 protons, 6 neutrons, and 6 electrons. the electrons would go around like this. So there'll be one energy level that has 2, and there'll be another energy level that has 4. And they orbit around each other around the nucleus. Nucleus being in the middle. According to Bohr's atomic model, I've already read this. So, the only improvement was that they're no longer on the outer shell or edge. They're now on specific energy levels. This is not the correct model of the electron. The correct model is the wave model, also known as the electron cloud model. Today's atomic model is, and Elena, lift your head up. John. Hit John. Wake up. Do not be sleeping in my class. Today's atomic model is base. Thomas.
You good? Can I use the bathroom, please?
Be quick. Keep Thomas, sit up all the way. Keep your eyes open. Today's atomic model is based on the principles of wave mechanics. According to the theory of wave mechanics, electrons do not move around in definite paths. Actually, an electron doesn't exist as a single particle. It doesn't have a specific spot. The correct interpretation is quantum mechanics. An electron is a fuzzy blur that can be in multiple. Thomas, keep your eyes open. Move your hand from your head. The electron is a cloud of probability. It could be anywhere in that probability cloud. One time you look at it, it's over here. Then you blink, and all of a sudden it's teleported somewhere else. It only exists as a particle when you're looking at it. When you're not looking at it, it turns into a wave, and that wave can be spread out over lots of locations. In fact, it's impossible to determine the exact location of the electron. You cannot actually determine an exact location of any object. This, from the quantum mechanics uncertainty principle, you can't know precisely the location and momentum of any object to infinite precision. So due to this uncertainty principle, it's not in an exact location. And so it doesn't move in a straight line or a certain deal. It actually teleports at sometimes. Instead, we think about it in terms of probability, statistics. We talk about the probable location of an electron based on how much energy it has. According to modern atomic model, an atom has a small positively charged nucleus surrounded by a large region in which there is enough electrons to make the atom neutral. And this is the electron cloud. The electron cloud is a space in which electrons are likely to be found. Thomas, wake up. Electrons whirl around the nucleus billions of times a second. They really don't move around the electron or the nucleus. They are not moving around in random patterns. Locations of electron depend on how much energy the electron has. Depending on the energy, they are locked into a certain area in the cloud. Electrons with the lowest energy are found in energy levels closest to the nucleus. Electrons with higher energy are found in the outermost energy levels, farther from the nucleus. So, doing a little summary. So Greek They and Dalton thought that the atom was indivisible. Thomas discovered the electron. Rutherford knew about the electron and nucleus and protons. Bohr knew about orbits. And Schrodinger knew about quantum mechanics and wave. Give Erwin Schrodinger the correctness for that one. Yes, be quick.
Yeah, very fast.
So, let me spell his name. You can give credit to Erwin Schrodinger for electron cloud model. So, the hydrogen is the most studied atom. Let me pull up the actual orbitals and show you what they look like. Put the phone up on silent. So this is the equation solutions for hydrogen, where the electron is in different energy levels. So this is 1s, this is 2s, they're spheres. This is your p orbitals. This is your d orbitals, and then this is your f orbitals. So let's see if I can find.
Why can't it be a little A? Why did it look like that? That's how God created them, dude.
So the s orbital is a sphere. The p orbitals are dumbbell shaped. Usually I draw them like this.
That little fishy.
They're more smushed in real life. Then we have our d orbitals. There are 5 of them. And then we have our f orbitals for the very high ones, the lanthanide series.
They look little gumdrops. Are we going on and like do the math of this?
I forget how far I go into it. So so here it shows the orbit. So here's like 2 hydrogen. Hydrogen would only have a orbital, s orbital, a sphere, and stop doing that. And here we have carbon. So this would be like 2 hydrogen and carbon bonding together. And trying to show it stacked on each other. Here. So we have an s orbital in the center, another s orbital surrounding it. So the bigger the energy level, the bigger these orbitals get. So dumbbell-shaped p orbital looks like this. S orbit inside the shell, and then S orbit in the second energy level. So the red is in the second energy level. This dark one, gray one, is in the first energy level. These p orbitals are in the second energy level. And this is actually the clouds. So every cloud, one way of defining a cloud is the electron cloud is the region where you have a 90% chance of finding the electron. So let's look at hydrogen with first energy level, which is a sphere. So we have a nucleus. So let's say we have hydrogen, 1 proton. And we look at the hydrogen, and we see an electron right there. We re-look at it, and it's teleported over here. We keep looking at it, and what happens is as we continually measure, we keep finding the electron in random different places, and we keep looking at it over and over. We'll eventually get this sphere where 90% of the time we found the electron in it. Here's an interesting one. So let's look at a single dumbbell, a p orbital. A p orbital looks like this, with the nucleus in the middle. So when we randomly look, we see the electron like this. Here's a question. How does the electron go from this side to this side?
Teleportation.
Yes. It just appears over there.
It drove.
It can't pass through the nucleus. It's just randomly over there.
No, it's got a twin node and then it's like it hides and everyone's over there. Look.
Trying to see if I can find.
We have 5 minutes in the class now.
Guys, I'm actually running on 6 hours of sleep from over the last 2 or 3 days.
Nice. Why? Like COD?
Fortnite.
Huh?
Hey,
Fortnite.
let's go.
I ran on like 5 hours of sleep last night.
Yeah, I went to bed at 6 this morning. Got up at 7.
My mom, uncle, and brother are out of electricity and water, and they've been coming over to my house.
Yeah, Fortnite single player, right?
No, but I haven't been able to sleep.
I can respect. If I get a box of ear, I'll put
Yeah, I'll be quick.
Yes. It's hard like checking me for 90 minutes, 80 minutes. My game finally came in yesterday, Saturday, Mr. Weather. After 2 weeks of waiting for them, they came in Saturday. It was Saturday. And I was so happy. I still think we should have done Call of Duty World War II over the weekend. You need to come over. Play a little more with me. That's us. You don't tell someone you come over, you act. Oh, you want to come over? Hey, you gotta come over. Hey, man, you're coming over?
Yeah, I guess that's it for today.
Coming over.